let's start off with number 1 here. Consider the reaction shown below. We're given some arbitrary elements with coefficients of 3, 2, and 2, and a 1. Express this rate of the reaction in terms of the concentrations of A, B, C, and D. So when I say express the rate of the reaction in terms of concentration, typically that's going to be in this format. So you're going to see delta concentration, I'll just use A in this particular case, over delta T. And what that tells me is that the delta represents change, as we know. Change. And change is always going to be final minus initial, right? So that's just, what this top part tells me is it's the change in the concentration of A over the change in time. So that says, if we were to write it out in full, well, it would be the final concentration of A minus the initial concentration of A over the time when we reach the final time here, minus my initial time. That would be the change in concentration of A over the change in time. Now, how do I relate that with what's going on here? Well, let's go get rid of this guy really quick. Okay, so how do I relate that to this particular question? Well, you can determine the rate of the reaction with respect to any of the constituents of the reaction. And what I mean by that is that I can define it with respect to A, B, C, or D, and they would all be equal. So you might ask, well, how do I accommodate for the coefficients that you see here? This A has just 1, but because there's only 1 of A and 3 of B, shouldn't it be much faster with respect to B because there's 3 times the amount? You would be right, and how we accommodate for that is you'll see soon. So express the rate of the reaction in terms of A, B, C, and D. We kind of got a hint on A. So the way I write that is I do the change in the concentration of A over the change in time. Now, because this is a rate that we want to be equal amongst all of our constituents of this reaction, well, naturally, because we have a reactant, we will have less concentration at the end than we had in the beginning because we're losing it. And I told you that change is equal to final minus initial. So naturally, if my final amount is smaller than my initial amount, then I'm going to get a negative number. Now, we want all of our numbers to be the same. So the way that we accommodate for that negative number is we put a negative here because the value inside these parentheses here is negative. So by applying a negative on the outside, we essentially multiply a negative times a negative, and it results in a positive number. You'll see why that becomes important soon. So that's how we demonstrate it for A. Now, this particular question asks us to do it with respect to A, B, C, and D. So we're going to do the same thing for B, C, and D. So remember, because of this coefficient of 3 in front of B, we're going to divide by 3 because we want it per mole of each of the reactants. Because, again, there would be the rate for B would be 3 times if we don't accommodate per mole. So, again, B is also a reactant, so it's going to be negative. And then we do the same thing. Change in the concentration of B over the change in time. And there we go. Now it's kind of plug and chug. Only difference now is that maybe I'll do this in a different color because they're different. They're reactant, or rather products. So then now I'll write this like this. So now with respect to our products, we can use positive values. And remember, at the end of the reaction, I will have more of the final amount than what I started with, which is my initial amount. So if your final is bigger than your initial, well, that results in a positive number. So because of that, I do not need to apply the negative number here. So all I have to do, though, is accommodate for the coefficient. So that's 1 over 2, the change in the concentration of C over the change in time, delta T. D has the same coefficient, so it's going to be the same overall rate. So that's also going to be a positive 1/2 change in the concentration of D with respect to time, as we see there. And currently, this seems like a fairly abstract kind of concept that you see here. But when we start attaching some numbers to this, it will make sense, hopefully, and you will see the value in doing something quite like this. So Let's get on to B. We'll close it out with C, and that'll be the first video for Chemistry 102. So let's do part B. At some point in the reaction, the concentration of B, and 13.2 minutes later is B as a new value for B. Based on this data, what is the average rate of the reaction during this time? Well, yeah, something I didn't quite say is that if we calculate the change in concentration over a finite amount of time, and what I mean by that is like some long stretch of time, for example, this particular case is 13.2 minutes, well, that means that we are getting the average rate of the reaction. So when we say determine the average rate of the reaction, I'm quite literally asking you to do the delta, in this case we're doing B, so it's going to be delta concentration of B over time. And we said that quite literally means concentration of B final minus the concentration of B initial over T final minus T initial. Now, we shouldn't forget that B, if we look up here, that B has a coefficient of 3. And previously we wrote that we had to accommodate for that by writing negative 1 over 3 on the outside. So we should do that. So that's going to be negative 1 over 3. And we'll see why that's a useful topic. Now, I should point out at this point that the delta T that we were referring to here is seconds. And I should point out that this B, the concentration, I've been kind of vague with it, the concentration refers to molarity. Molarity. So that's molarity, just to remember, that's moles per liter. Now, this is important because if we look at the question, we see that at some point the reaction for the concentration of B is this number, and 13.2 minutes later, minutes meaning the main thing here, minutes, it becomes this particular concentration. So that is not in the format that we need it to be. So we very first need to accommodate and turn the 13.2 minutes into seconds. We know that for every 1 minute, there is 60 seconds. So a quick calculation. Let's do that really fast. 13.20 times 60, we get 792 seconds. Cool. Hopefully you understand really why we need to do that, because the convention is that we normally use seconds in the bottom. And I think your answer would not be wrong, but you would have to demonstrate that your rate is with respect to molarity per minute, not molarity per second, which is the normal convention. So let's continue. We're basically going to plug our values that they gave us in the equation into this equation that we see here. So let's do that. So negative 1 over 3. We're going to put a nice little fraction here like that. My concentration at the end, or B final, that would be this smaller number here, 0.9746. And I know that because, well, B is a reactant in this reaction. So as the reaction proceeds, the reaction should, because we're going in one direction in this case, get smaller. So because of that, let's plug in that value here, 0.9746 molar minus our initial concentration, which must be the other B that we see here. That's going to be 0.9986 molar. And let's do that with respect to time. So then let's assume that I'm starting at T equals 0, so 0 seconds, meaning I start the clock and then 13.2 minutes later I measured it again. So my initial time must have been 0 seconds. So if we do that, my final time was 792 seconds, and I'm subtracting 0 in this case. So we're almost done. Let's plug this value in. I do want to point something out really quick of the importance of adding this negative that we see here. Now, let's see why we did that, because if I get the difference between these two values here, I will get a negative number, and you can kind of see that. So because it's 0.97 and I'm subtracting 0.99, so I'm going to get a negative number as a result. So we accommodate for that by adding that negative on the outside, like I said earlier. So let me plug this in really quick. Make sure to add that negative out there. Boom. Okay, so that's going to be 0.99746 minus 0.9986 over 792. And let's see what I get. All right, my answer is, and notice my units are still fine. I'm going to have molarity on top and second on the bottom. So my answer is going to be, if I put it into scientific notation, account for significant figures, which in this case is 4. It's going to be 1 point, let's see, get my pencil up, 1.010 times 10 to the negative 5 molarity per second. And that's equal to my rate of the reaction. So you can see that negative is fairly important so we can get a positive value at the end. Okay, let's finish off this last part of this problem. In one experiment, the rate of change of B was found to be 2.5 times 10 to the negative 4 molar per second. What is the rate of change of C in this experiment? Now, we're going to kind of use the topics that we talked about in the first part because the rate should be the same for each of these per mole. But if we actually accommodate with respect to their coefficients, their rates will be different to some degree because I have more of some than I do the other. So let's figure this out. So earlier we mentioned that B and C have this particular relationship. I'll point it out right here. This particular relationship here, that 1/3 of the concentration of B is equal to 1/2 the concentration of C over with respect to time. So let's bring that down because that's what we're equating at this particular point. So that's negative 1/3 delta concentration of B over the change in time is equal to, is 1/2, right? Yeah, 1/2, positive 1/2, the concentration of C. Let me fix that. Delta C with respect to time. Now, in one experiment, the rate of change of B was found to be the 2.5 times 10 to the negative 5 molar per second. Now, what's the rate of change of C? Well, what I want to essentially just do some algebra and isolate C in this case. So how do we do that? So let's do that really quick. So multiplying 2 on both sides, 2 over 1 times 2 over 1 right here, we will eliminate the coefficient on this side. So if we do that, we'll get a new equation, and we'll get negative 2 over 3 delta B over delta T is equal to the change in the concentration of C with respect to time. So you can see then that we've essentially isolated the delta C over delta T, which is the rate of change as we see it. So whenever a question asks for the rate of change with respect to one variable, and they give you another variable, set them equal to each other because the rates should be equal in a chemical equation. And now all we have to do is plug in our values. So let's do that. So then the value for this B, like delta B over delta T, is going to be that 2.5 times 10 to the negative 4 value. And then all we have to do is multiply it by 2/3. So let's do that. So we're going to have 2 over 3, 2.50 times 10 to the negative 4 molar per second. We can kind of get rid of the negative because this particular rate already accommodated for that. So now just getting our answer really quick, 2.50 times 10 to the negative 4 times 2 over 3. That gives us our value here of 1.66. I have 3 significant figures, so I'm going to go to 1.67 times 10 to the negative 4 molar per second. And that's going to be the rate of C in this case. So I'm going to put rate rate of C.